Okay, we're going to look at partial oxidation of alcohols. So primary, secondary, and tertiary alcohols can all be oxidized, but as you can see on the screen here, they all form slightly different products. So I'm going to demonstrate the three different types of alcohols and their reactivity. So I'm going to start with what says ethyl alcohol, but we just know this as ethanol, so there's the structure. All right, next up, I'm going to look at a secondary alcohol. So again, isopropyl alcohol, which is more formally known as propan-2-ol. Okay, so the alcohol occurs on a secondary carbon, right? And there's a structure. And finally, we're going to have a look at a tertiary alcohol. So this is tert-butyl alcohol. We would know this more, it's more formal, but our naming system would call this 2-methylpropan-2-ol. All right, and then we'll get a structure for that as well on the screen there for you. All right. So what we need is potassium dichromate. Okay, the dichromate ion, so Cr2O7 2 negative, is a very powerful oxidizing agent. This could also be done with the permanganate ion. Okay, either way, you can see there's a very bright orange color formed from this. Okay, so when an alcohol reacts with an oxidizing agent, okay, the alcohol itself, those carbons are oxidized, and the oxidizing agent, remember, is reduced. So chromium in the 6+ oxidation state is going to form a chromium 3 when it's reduced, and chromium 3 is a very dark green. So I will look for the color change. The dichromate solution must be acidified. You must specify this in any testing type scenario. So from left to right, there's Schofield, say hello. From left to right, you have ethanol, propan-2-ol, and 2-methylpropanol, and you can watch the colors change. All right, now the extent of the reaction will change depending on whether it's refluxed or not. So reflux means basically to boil and recondense. All right, so as you can see, my primary and secondary alcohols have reacted, but my tertiary alcohol, I still have that dark orange color of the dichromate ion. So that, to me, that's the indication that no reaction has occurred there. All right, so I'm going to test the pH of what was ethanol. Okay, this is going to come back red on a pH strip. This is ethanoic acid now. All right, so this is the full extent of the reaction. All right, my second test tube there, which was propan-2-ol, is now propan-2-one. I'm going to test this for acidity. Okay, so you can see that there's none, so no matter how long I reflux it, nothing happens. So let's have a look at what the actual reactions are. All right, you're going to need the reactions, primary, secondary, tertiary, and the conditions. All right, the conditions is an oxidizing agent and either reflux or not. So we're going to look at 3 different isomers of C4H10O. So these are all types of butyl alcohol. So first we'll look at a primary alcohol. So this will use butan-1-ol, more commonly known as N-butanol. Okay. Now a secondary alcohol, which will be butan-2-ol. So again, our hydroxyl functionality will be on the second carbon. Okay, correct name there. Tertiary alcohol. Okay, so that means I need a tertiary carbon. All right, so this is going to be. Just clean this up a little bit here for you. So we'll have a tertiary carbon here, and on that is the hydroxyl group. All right, so this will be 2-methylpropan-2-ol. So you might be able to look and deduce why, though, if you were to go back and see the extent of the reaction in the previous video, the color change, you might be able to figure out why primary, secondary, and tertiary react differently. So acidified potassium dichromate and a primary alcohol will produce the corresponding aldehyde, as you can see there in the structure. Acidified potassium dichromate, or acidified oxidizing agent, and will produce a ketone from a secondary alcohol. Right, and this all has to do with number of bonding sites available on the carbon. Right? As you can see in a tertiary alcohol, that tertiary carbon is already bonded to 3 other carbon atoms. It can't form an oxidized double bond to, it can't form a further oxidized species. It can't form a double bond with any oxygen. Right? All the bonds are used, and it can't further react. So it doesn't matter how much we heat it, reflux it, anything like that. A tertiary alcohol will not react. All right, I'm just going to replay the video up here in the corner of the reaction itself. So butanol, if I reflux it, so if that means to heat basically under boiling conditions, all right, will eventually form butanoic acid. All right, and that primary carbon has all those bonding sites available to it. All right, it can exchange the hydrogen, the bonds it has to the hydrogen for more bonds to oxygen. All right. Butanone, however, doesn't matter how much you reflux, it can't further oxidize. All right, so it can't bond with any more oxygens because it's already bonded to 2 other carbons. All right, and T-butanol, it doesn't matter, can't react anyways, so you can heat it and heat it and heat it and heat it and heat it, and you'll still get no further reaction. All right, we're going to take this time and we're going to have a look at the actual oxidation states just as a good review for redox chemistry. Okay, you need to know the reaction conditions and the difference between primary, secondary, and tertiary reactivity. As a little refresher here on oxidation numbers, I'm just going to work this up so you can see what I mean by partial oxidation and the effect of the chromium-6 ion. So I would highly encourage you to go and try to assign the oxidation numbers in butanol. You find that they're -2 for butan-1-ol, -2 for butan-2-ol, and the tertiary alcohol. You'll find that in butanol and butanone, carbon's oxidation state is -3/2, whereas in butanoic acid, it makes it all the way up to -1. All right, this would be a great activity just to refresh yourselves. It's often paired up. Redox and organic chemistry are often paired up on the final exam under this type of scenario.